This is a particle podcast. WA Science told different. Powered by Scitech.
Please Look Up is recorded at Scitech on Whadjuk Noongar land. Good evening, everybody. My name is Leon.
And I'm Amanda.
And welcome to a special episode of Please Look Up. In this episode, we're talking about the Polar Satellite Launch Vehicle debris that washed up in Greenhead in July 2023, which has just been announced will be on display at Scitech. You've probably seen it in the news, and in this episode, we're going to tell you what it is and what it does, how it got here, and we're going to talk about a lot of interesting things along the way. So thanks for being here, Amanda.
Thank you for having me. Yeah, it's pretty exciting. At Scitech, we've been hearing about the PSLV. I get them wrong way around. I always know where P and V go, but the middle letters confuse me. So PSLV, shall we start with what it is?
Yeah.
Yes. When to me it sounds like a sex thing. PSLV.
PSLV.
I think because there's a P and a V, and then it's just a bit spicier in the middle.
Okay.
I've asked other people about this. They agree with me.
So that's going to be the subtitle of this episode now.
PSLV, is it a sex thing?
Yep.
In short, no. It can be one of those summary clickbait things where it's like, is it a sex thing? No. Some people think it sounds like a disease as well.
Oh, wow.
It's none of those things. It's,
No.
as we said, Polar Satellite Launch Vehicle.
Yeah. So I kind of answered that right in the intro before even calling it the PSLV. But that's what we'll be calling it from now on, because Polar Satellite Launch Vehicle is quite a mouthful. Mm-hmm. But yeah, so the Polar Satellite Launch Vehicle,
Or PSLV.
or the PSLV, is a full-sized rocket that's it's launched and operated by the Indian Space Research Organisation. So it's a medium-sized rocket, and it's designed to put satellites, medium-sized satellites, about the size of a car, into orbit, into low Earth orbit around Earth, and most of those orbits are at very sharp angles to the equator, so they go very, very high north and very far south, which take them over the poles. And so those sort of orbits are called polar orbits, and a satellite that follows a polar orbit is called a polar satellite.
So we have the Polar Satellite part of the
Yeah.
PSLV.
And
So
yes, so
what's the LV?
Well, the LV is the whole rocket. So you need a whole rocket to launch these satellites into polar orbits, and so that's the whole rocket.
So it's the launch vehicle.
Yes, the launch vehicle. And then the bit that we've got is part of the PSLV. It's actually only a small part of it. So the full-size PSLV is 44 metres tall, and the bit that we've got is the third stage fuel tank, which is about just over 2 metres by 2 metres. So it's quite a small piece. Well, it looks big when you're standing next to it, but it's actually only one small piece of a much larger launch vehicle.
Yeah. So I obviously heard about this news. I think everyone probably heard about it last year when it washed up on the shores of WA.
Yeah, I think it was like in the international news as well.
Yeah, it was pretty big. It was pretty exciting. But do you want to walk us through how it's going to end up here at Scitech from being washed up on the beach up north?
So being washed up on the beach. Well, obviously the first thing was to actually figure out what it was, because
there were a lot of theories going around.
Yeah, some of them pretty wild. Although some Redditors hit the nail on the head pretty quickly. I remember seeing a Reddit post a day or two after it was there, and there was some photos of the equivalent brand new piece and then this piece of debris. But yeah, so the Australian Space Agency sort of stepped in, because you can kind of tell even just by looking at it, oh, that looks like a piece of a spaceship, because it literally is. Yeah. And so the Australian Space Agency was there, and they worked with the Department of Defence and the WA Police Force, firstly to sort of set an exclusion zone just to check that everything was safe. And then
it wasn't alien.
Yeah, it wasn't alien, anything like that. And they got in touch. They have relationships with the Indian Space Research Organisation, and confirmed that it was indeed from a Polar Satellite Launch Vehicle. But then there was also some inspections to be done. So the WA Museum was involved in collecting samples from it to figure out what it's made of and is it safe to approach, and performing chemical analysis on it, looking for hazardous materials, dangerous chemicals, things like that, because rocket fuel can be dangerous to work with. Rocket materials are not commonly purchasable, things like that. And so a lot of different people were involved, a lot of organisations, and eventually it got the all clear that it was safe to approach. It needed some work to clean and preserve, and then it was loaded into the back of a truck and shipped down to Perth, driven down to Perth by a couple of Scitech staff. They hired a truck, drove out there, put it on the back of an excavator, into the back of a truck, and down it came.
Yeah. So it was pretty early days, though, that it was decided, like, that Scitech kind of won the right to display it. It has, I mean, I've seen a lot of articles in the past week because we put out the media release that we have it, but there have been all these articles being like, oh, after months of being in limbo, we finally know, like, it's been sitting in a warehouse in limbo, not knowing where it's going to go, but it's not quite the case. It's been in a warehouse for months, but we have known it's going to be here for quite a long time.
Yeah, I think I found out in January.
Yeah.
So yeah, like I don't think straight away it was known. In fact, probably not. Like it probably stayed.
It didn't rock up on the beach and we went, that's ours.
Yeah.
There was a process.
Yeah, but I think we found out about January, and yeah, we've sort of been working towards it since. We didn't just learn all this stuff about it last week when the minister announced it.
Yeah.
But yeah, as for between there, June, July and January, as far as I'm aware, it was just in a warehouse up in Kuro, and I believe. Sorry, guys. I think the Shire was really keen on keeping it up there.
That's all right.
There's
plenty of good reasons to go up there.
Beautiful beaches.
Yeah, exactly. Who knows? You might find the next thing that washes up on their shores.
Well, it is worth pointing out, this is slightly off topic, but SpaceX have been ditching parts of their Starship rocket into the Indian Ocean. So there's a good chance some of those might start washing up on our beaches soon.
Musk's junk just landing on our shores.
I have already asked the Australian Space Agency if any bits of that wash up, if we can have it as well, but they ignored that question.
What makes that not just straight up pollution?
There's no real answer.
Next question.
Well, no, space junk is a very big problem, both in space and on the ground. And it's a much bigger problem in space than it is on the ground. Most of it just sinks. It's a miracle, at least as far as I'm aware, that this thing floated and stayed in one piece. Because if you look at the barnacle growth on it, it looks like it's been drifting for a number of months, if not years. So, yeah, I'm surprised that it maintained its composure and held itself together.
So modern shipwrecks aren't the old ships on the sea; they're actually rocket ships that have ended up.
Yeah, I guess so.
Cool. Okay, so it's ended up here. What I've been actually interested in is how much work has had to go into displaying the object. I think sometimes we think something like that. You're like, yeah, just whack it. It's just going to be in the planetarium foyer. So it's not even like you don't have to buy a ticket to come to Scitech to see it. It is just going to be on display as a free to view thing. If you're not interested in coming in while you're there, you might as well come in. But if you don't want to, you can just come have a look at it. It's just in our foyer. But there's actually been a lot of work into preparing it and actually preparing the space. I was just talking to our Osh guy last week and he even talked about having to figure out how much weight the ground in the foyer can bear to actually put down the exhibit we need.
Yes. Yeah, that's right. A lot of stuff that you don't realise goes into it.
Until you talk to the safety guy and he's like, you're like, why don't we just do this? And he's like, here's why. And you're like, oh, okay.
Yeah. Well, that's right. And so as I sort of mentioned, it had to go for chemical analysis to be determined that it was safe.
Yeah.
And yeah, we had to take advice on. And interestingly, we originally the footprint of the display was planning to be about 3 meters across, but then advice came through that that's still a little too close for comfort for people to reach over and touch it, and it's recommended against that. We weren't too worried at first, but the advice from preservation experts said no, you probably shouldn't let people touch it quite so easily. So that we had to expand the size of the footprint to make it harder to reach. We've had to run additional power cables all through the walls of the planetarium foyer, which is quite interesting. As we record this right now, the pallet, the base that it's sitting on is being constructed. Even down to the, we wanted people of all ages to be able to see it, obviously, so we've had to surround it in fencing of some kind, and we ended up having to settle on a very specific type of glass.
Oh, the story behind the fencing was big as well. Like it, so I heard from the project manager how many different meetings they had about the particular type of like plexiglass or whatever it's called that goes into the fencing that has to be able to take the weight of a crowd in case something happened. Yeah,
that's right. And if there's a problem, it's not going to, if it fractures, it won't be
it can't
the dangerous
break or
type.
hurt anyone. Yeah,
so all these little things that when you're just standing there looking at an exhibit going, oh, well, it's cool to look at. But then, all these little things have been thought of so that you don't have to think about it. Because if you go there and there's obviously loose cables and hanging fabric, you're like, well, I noticed that.
Broken glass everywhere.
But the best parts of the design are the bits you don't notice. We have also prepared some beautiful graphics to go alongside it.
And Leon's been working very hard. There's also a video there.
Yes.
So in case you've been listening to this podcast and never heard me and go, I wonder what Amanda looks like, you can go see my video. I did. You'll be like, that's Amanda.
Yes, I was about to say, would you like to tell us who the star of that video is?
Oh, me. I don't even have to give me that opportunity, right in there.
So, yes, that's right. So some printed graphics, a video, and also a huge sort of art piece that's going to run down the staircase, showing what we think happened to this object as it fell from space and made its way to Australia.
Kind of talking about its journey to get here.
Yeah, that's what we really wanted to focus on with our communication is its journey. That there's any number of places you can take the communication around this exhibit, but we decided really want to talk about it because it's from India. Getting from India to Australia is already a hell of a flight. Yep. But then if you detour via space and spend a few years in the ocean at the same time, it's all the more remarkable.
Yeah, and that was a really interesting part when you think about how much time would have gone into building this fuel tank as part of this rocket, and the purpose is to go to space. And it did, not all fuel tanks go to space. So if we think about how this rocket would have worked, it burns in stages the way a lot of rockets work. So it would have burnt off stage 1 and stage 2, and those stages wouldn't have made it to space. But stage 3 would have still been in the rocket when it got to space. Mm-hmm. And then it kind of uses up all the fuel in its third stage, and then that third stage is jettisoned back to Earth, and the rest of the rocket continues out into orbit around Earth. So then stage 3, this fuel tank that we have now, would have made its way back down to Earth and been in the ocean a while and then washed up on our shore. So it was designed just to go to space, but actually only spent a very small amount of time in space.
Yes, that's exactly right. And I looked up a whole bunch of the flights of this rocket. So there's been 60 launches of the PSLV. And and in every single one of them, you're right. The third stage is definitely not supposed to stay in space. They're always supposed to fall back down. So
there's about 60 somewhere.
There's about 60 somewhere. I reckon.
We're not sure which one this one came from yet.
No, and if we knew, it would make it so much easier.
All the graphics requests coming in, being like, how far exactly did it travel? And we're like, we don't know exactly.
Sure. No, but on every single one of them, the third stage fell back down into the ocean from a height of at least 300 kilometres.
Yes, so, well past the Kármán line, which is the imaginary line where we say this is now in space.
Yep.
So
yeah, which is 100 kilometres. Yeah, that's right. Yeah, as you go up, space doesn't really have a sharp edge, but the atmosphere just gets thinner until it basically might as well not be there.
And 100's a nice round number to work with, so we go 100 kilometres up, you're in space.
Yeah, unless you're in America and you use freedom units, in which case you round it off to 80 kilometres. Because America's weird like that.
80 kilometres or 80 miles?
50 miles.
50 miles?
Yeah, which is 80 kilometres.
Really? I didn't know that they had a different line. I just figured it would be a conversion of 100 kilometres.
No.
Look, I'm learning things.
Everywhere else in the world is smart, and America uses 80 kilometres as the boundary for space.
So if you want to say you're an astronaut, launch from America, you don't have to go as far and you can claim to be an astronaut.
Pretty much. But so that's right. So this object that we have has fallen from at least 300 kilometres up, which is pretty
undisputably
nuts.
Space.
Yeah, undisputably space. And so it's amazing it even survived in one piece. And so, as I said, where are the other 59 of them? I reckon they're at the bottom of the ocean, is my hypothesis. And I looked at a bunch of these flight profiles, and there's sort of two main launches that this rocket does. So the rocket launches from the southeast coast of India. So if you imagine a map of India in your head and it's shaped like a triangle that points south, so it's launching from the southeast coast, which is from above the right-hand side. And so some of the launches, they sort of follow out naturally from the side of that triangle. They go out over Indonesia, and the rocket stages fall off at exactly the right time so that they don't land on anywhere in Indonesia. And the third stage actually lands in the Pacific Ocean. And that is one possible location that it might have come from. But getting from the Pacific Ocean to Western Australia by random current is very unlikely, in my opinion. It's not impossible, but it's very unlikely. What I think is much more likely is the other, much more common launch that the PSLV does, which is it takes off from India in the same direction. It's sort of leading out to the southeast. But then what it does is it swings a big right-hand turn and goes all the way down south past Sri Lanka and then down to the southwest. And the reason it does that is so that all of these empty fuel tanks don't land on Sri Lanka. And so instead it swings around and then it goes to the southwest. And the third stage fuel tank ends up in the southern Indian Ocean. And that's where I think it's much more likely to have originated.
Yeah, especially onto the West Australian shore.
Yeah, it's pretty straightforward, at least I think. And if you look at the ocean currents and the wind speed, the prevailing winds, the roaring 40s as they're called, down in the southern Indian Ocean, I found this out recently. There's the Roaring Forties I remember reading about, which are sort of for about 40 kilometres south latitude, and they blow from west to east, so they blow from Africa to Australia. And that's kind of where this thing splashes down. I didn't know that if you go further to about 50 degrees, they get even stronger, and they're called the Raging 50s.
Excellent. No, I didn't know we were naming winds besides, the Frio Doctor. So there you go.
Well, I guess there you go. You can quite easily imagine this thing drifting to Western Australia and then getting caught up maybe in the Lewin Current and then eventually making its way to shore.
Yeah, that makes sense. So we've kind of talked about the journey this particular little fuel tank's been on. But we've said, its purpose was to go to space, but obviously it was to launch a satellite, a polar satellite in particular. But do you want to talk about what in particular ISRO is looking to do with these satellites?
Yes. So India has this very big science program called the Indian Resources Satellite Program, which is to launch many, many satellites. They've launched 35 of them so far into polar orbits to study mostly India from space for the purposes of benefiting the country, but also that these satellites, they see the whole world. So you can, if you're nice enough to India, you might ask them for some data and they might cooperate. And there's any number of reasons. So some of these satellites are specifically looking at forest growth, for example. They can look at the size of forests and estimate if there's hot summers and fires. They can estimate how large the fire will be, or if it's a rainforest, how much lumber you can sustainably get from it. Some of them look just at farming. They look at moisture content in the water, and farmers can figure out how much irrigation they need. Some of them are used for mapping cities, and so they can see India is a very, very populated country with very large cities. So urban planners can use this satellite data to plan city growth, and even things like disasters and earthquakes and recovery. You can get big citywide images from space to help you recover from those. And so that's this big program that multi-decades that the Indian Space Research Organisation has been working on. And that's why they built the Polar Satellite Launch Vehicle, to launch these satellites into these orbits.
Yeah. I mean, we sort of touched on the orbits earlier when we talked about what a polar orbit is, and these satellites are polar satellites, so they go into polar orbit. But when you're talking about all those projects that this research organisation is working on, why in particular do they want a polar satellite to gather that data? Why can't you just use any random orbital path?
Yeah, good question. The answer is very subtle. And because you're right, any satellite could technically do the job as long as it passes over India at least once an orbit, or once a day, or whatever. And the particular reason is that satellite orbits, they actually drift. So imagine a satellite that passes over Earth over Perth City at 10 o'clock today, and then imagine it's time to be perfectly in line to pass over Perth at 10 o'clock tomorrow. There's a problem, though, is that at 10 o'clock tomorrow, the satellite will actually be slightly off. It'll be off to the west. And that's because satellite orbits drift. And it's because Earth's gravity actually pulls the orbit sideways. And the amount that Earth's gravity pulls your satellite sideways depends on your angle to the equator. There's a lot of complex physics that goes on. But long story short, if you get your satellite at exactly the right angle to the equator, specifically 97 degrees, so you're actually orbiting in the opposite direction to Earth's rotation, your orbit will drift in such a way that it cancels out the Earth's gravity that's pulling it sideways, and you pass over the same spot every day at the same time. So, and that's really useful, because if you're measuring the temperature, say, at 10 o'clock today, you can't meaningfully compare that to the temperature measured at 5 o'clock yesterday, because the time of day makes a difference. But if you can get satellite measurements at 10 o'clock every day, every year, for as long as the satellite works, you've suddenly got really, really consistent data. And that is a very specific orbit, and it's a polar orbit.
Yeah.
And that's why they're polar satellites.
Right. So this particular vehicle obviously launches polar satellites. But one thing that was really kind of meaningful for me when I was looking at it is that we use satellite technology for so much of our life, and they're not all polar satellites. They can be satellites in all different orbital paths. But often I mean, often we don't even think about the fact that there are satellites powering every time you use the internet or look up your location on Google Maps or order Uber Eats or anything like that. That's all powered by satellite technology. But more importantly, I don't even really think about the fact that every time we're using a satellite, a rocket was required to put that satellite into space, and all the work that goes behind getting satellite technology, which is kind of a daily part of our lives now.
Yeah, it's very hard to remember that. It's just out of sight, out of mind, and especially in Australia where we don't have a active launch program. That might change soon, but yeah, you're right. And of course, given that most of the rocket launches are designed to be as undisruptive to people as possible, for example, ditching their spent stages in the ocean, that's right, they go out of sight, out of mind. But yeah, there's more than 6,000 satellites up there now, so that's 6,000 rockets at least.
Yeah, I mean, it's quite a lot of satellites, and this is one fuel tank.
Sorry, I just realised 6,000 satellites doesn't necessarily mean 6,000 rockets. But
no.
Sorry,
for example, Binner. But yeah, so it's still a lot of rocket ships. And then if we think about this one fuel tank that's washed up, it's all that space junk. And we were sort of talking about kind of the pollution it creates. For example, the perspective here on Earth, if we're just dropping fuel tanks into the ocean. If they're spent, they don't seem to be causing any issue and they sink to the bottom of the ocean. Maybe we say that's not causing an issue, but not all space junk does come back to Earth. Some of it stays in orbit around Earth. And what are the sort of implications for the space junk we're putting into orbit and leaving in orbit?
That's definitely a case of the global answer to that is a bit like the global answer to climate change, which is if we ignore it long enough, maybe it won't be a problem. And then all it does in the meantime is it gets worse.
Great. So if we leave it and it becomes a much bigger problem, we reckon we'll be able to tackle that much bigger problem 50 years down the road?
It's for the children. Yes. That's the sort of cynical take on it. Yeah, at the moment, space junk that gets to orbit, yeah, that's right, not all of it falls back down. And because there's no atmospheric drag, because it's above the atmosphere, it stays there for years, if not decades. There is a tiny bit of atmospheric drag. Eventually it falls back. But yeah, you're talking decades. And at the moment, there's no real coordinated international plan for getting rid of it. There are any number of ideas and startup companies and plans and projects and some governments are sort of coming around to the idea that maybe we should do something about it. But yeah, at the moment, there isn't really a coherent plan. And that's because there's no real easy way of doing it apart from prevention in the first place. So if you don't put junk there, then obviously it's not a problem.
Oh, that's a good one.
It's a bit like plastic. Recycling plastic only does so much. Really, the best way is to stop it there in the first place.
So why don't we just not put junk up?
Yeah, part of it is big sky theory. That it's this idea that space is just so big. If you had two cars randomly driving across Australia, they could drive across Australia for 1 million years and never hit each other. Mm-hmm. That was the sort of the thinking, failing to really think it through carefully. That satellites move a lot faster, they cover a lot more area a lot quicker, so they intersect each other a lot more often.
Because there have been collisions.
Yes, that's right. And if they do collide, the collisions are a lot more violent.
Mm-hmm. And they produce all these different pieces of space junk.
Yeah, they produce. It's a self-multiplying problem.
Yeah. And so obviously once they're smaller, more difficult to track and.
Yes, that's right. And yeah, it's an exponential sort of growth. The smaller they are, it's half the size. It's not twice as many. It's 100 times as many. The estimates are that there's probably about 3,000 dead big satellites, the size of a car. But there's probably 130 million pieces of space junk that are the size of a nut or a bolt or a screw. And those ones, you can't even barely see them from Earth. The moment you discover them is the moment your spaceship gets hit by one. Yep. And there have been examples of spacecraft getting impacted by space junk.
I know the ISS has to make corrections in its orbit to avoid space junk.
Yes.
Obviously, they're looking at bigger pieces that they can easily track and avoid.
Yeah, you're 100% right. There's some photos of some space shuttle missions where I think like a speck of paint, like smaller than a millimetre, hit one of the windows of the space shuttle, and there's a huge crack in this 15 centimetre window, and that's just a speck of paint. Yep. And so, you can imagine even just something the size of a tennis ball moving at 27,000 kilometres an hour. You look at when there's a little fender bender at 40 kilometres an hour, the whole bonnet's crumbled in. Imagine what's going to happen at 27,000 kilometres an hour. There's no real easy answer to solve the space junk problem, and as a result, the international cooperation is only just sort of waking up to the fact that we need to solve this problem. So I'd love to be able to say, here's how we're going to do it, and here's how we're working together. We just can't at the moment. So the best part is to just avoid it in the first place. As we said, the third stage exhibit that we have here at Scitech it's not designed to stay in space. It just physically cannot. It can't get fast enough. However, the fourth stage of the PSLV does get to space, and it does stay in space as space junk. However, what they do is they move it to what's called a graveyard orbit, where they use its last little... It deploys its satellites, and then whatever fuel it has left, it uses that to push itself out of the way into a space where there's no other satellites. So it's a mitigation attempt, I guess you would call it.
So there's less sexy orbital paths then.
Yes.
So the polar satellite, the polar orbits are one orbital path. Are there other particularly more popular orbital paths?
There's definitely those low Earth orbit ones. That's the most populated. So a polar orbit is an example of a low Earth orbit. And polar satellites are those ones that have very high inclinations we spoke about. There's these lower orbits. Low Earth orbit in general is very, very crowded.
So when we talk about low Earth orbit, they're satellites that are closer to Earth, so they're lower.
Yeah.
How far up are we talking?
Less than 1,000 kilometres, basically.
Okay.
The International Space Station is typically about 450 kilometres up, and that's a pretty good distance. But at that distance, a satellite will fall back to Earth in maybe 10 years.
So Hubble, is that in low Earth orbit, the Hubble Space Telescope? Is that
the Hubble telescope is a bit higher up.
Okay.
So that's about 700 kilometres up. Mm-hmm. And interestingly, you go up a few hundred more kilometres, and Hubble will stay up at that altitude only was put there in 1990, and it will probably stay there for another 15 years before it starts to fall back, if it even works that long. But so low Earth orbit is very popular. The other really crowded orbit is what's called geostationary orbit, which is an orbit 36,000 kilometres up.
Very specific.
Yes, very specific, that sits exactly above the equator. And the reason you want to do that is because if you're 36,000 kilometres up, the time that it takes you to orbit the Earth is exactly 24 hours.
So the same time it takes Earth to orbit.
That's exactly right. Well, to spin, yeah. So if you're...
Oh, right. Rotate, not orbit.
So if you're exactly above the equator, at that distance, you will orbit the Earth once in 24 hours, and the Earth will spin once in 24 hours. And
why is it that it's 3,600 kilometres up?
36,000.
36,000. Wow, so a lot.
Yep. It's...
Because if I'm on the surface of Earth, I'm taking 24 hours to orbit Earth.
Yes, good point. That's because you're on the surface, and the surface of the Earth kind of drags you and everything around with it. Mm-hmm. You're not orbiting the Earth. Mm-hmm. In fact, the reason satellites in low Earth orbit travel at 27,000 kilometres an hour is because that's how fast you need to travel to not fall back to the ground. Because orbit is... I'm going to quote badly Hitchhiker's Guide. It's a way of throwing yourself and missing the ground.
So we're just sort of travelling in a straight line, but then we keep falling back to Earth at the exact right rate that we're just going round Earth, but we're not leaving the orbit and we're not crashing back to Earth.
You've nailed it perfectly. It's actually a very subtle concept, You move sideways just fast enough so that when you fall down, the Earth has fallen away from you because of its curvature. Now, obviously, the closer to Earth you are, the stronger gravity is, and so the faster you will fall. And so when you're really close to the Earth, you need to be travelling 27,000 kilometres an hour, and that means you orbit the Earth 16 times a day. Whereas if you're a lot further out, for example, 36,000 kilometres above the surface, gravity's a lot weaker, Earth's gravity's a lot weaker, and so you fall slower, which means you don't have to move quite so fast, and so you can move a lot slower. And the maths has been worked out, and it's worked out that at 36,000 kilometres an hour, you will need to move at exactly the same speed as the Earth does, and to rotate once every 24 hours.
Yeah. And so how are those satellites moving? Like, do they still have fuel they're burning and having to continually keep themselves moving at that speed out there?
No, this is... we have Isaac Newton to thank for this, which is Isaac's first law of motion, which is...
Not the equal and opposite one. It's the staying in movement.
Yeah.
An object in motion stays in motion.
Yeah, an object in motion stays in motion.
I got there in the end.
Yeah. So it's not, and well done for Newton to figuring this out, because it's not immediately obvious. Because if you take your foot off the accelerator in the car, your car will eventually come to a stop. you need to keep applying the accelerator and you need to keep burning fuel to keep your car moving. But
to be fair, he didn't have cars back then, so he probably wasn't confused by that example.
Well,
so
yeah, exactly.
maybe that's how he could figure it out.
Yeah, exactly. But it's understandable why it might be confusing. But the reason the car stops is because there's wind resistance and because there's friction with the ground from the wheels. But in space, there is no wind resistance or friction with the ground. So the idea is you get the spaceship moving by using a big rocket. But once it's moving, it's actually never going to stop moving. It might hit something, or any number of things can happen. But the actual movement it's baked into the object now until that energy gets spent elsewhere. And so you very carefully burn exactly the right amount of fuel to get the satellite exactly where you want it and moving exactly the way you want it to move. And then you just turn the engine off and it will move like that forever.
So how come they fall back to Earth after decades?
Well, the ones that are closer down, like in low Earth orbit, like the International Space Station, remember we said that Earth's atmosphere gets thinner as you go up. Mm-hmm. It never really quite, at low Earth orbit of a few hundred kilometres, even though you're above 100 kilometres and you're in space, there's still just the barest amount of wind resistance. Like, not so much that you would feel it if you stuck your hand out the side of the spaceship.
Breathe it
in. Yeah. It's not enough to breathe it in or to feel it. But when you're travelling 27,000 kilometres an hour, it's just enough to slowly, over a period of weeks, months, years, slowly drag the satellite and slow it back down again, and it will eventually fall back to Earth. But out where the geostationary satellites are, 36,000 kilometres up, they're basically going to stay there forever. The only way to get them out of there is to move them out by firing their engines and using fuel. So they do have fuel on board for if they need it, but yeah, they don't use it to keep pushing themselves forward. They only use it if for some reason they start to drift and they need to, oh no, I'm drifting, move back. It's called station keeping.
So these ones in geostationary orbit, they can stay above a certain point over the course of years, just watching that certain point on Earth.
Yep.
They are spying on us, or what's their situation? What are they doing?
Yeah, I have no doubt some of them are spying. Those are the ones you don't hear about. Yeah, probably. But also for weather forecasting, for example. Interestingly, so yeah, when you see those beautiful pictures of Australia on the news every night, where you look at the cloud maps and all of that, those are coming from geostationary satellites. So yeah, when you see cyclones and hurricanes and big weather things, that's what they're for. And interestingly, Australia doesn't have a satellite there to look at us. So all of our images from Australia that show the weather are coming from a Japanese satellite, because Japan has a geostationary satellite. Right. And obviously through data sharing agreements, that's how we get our sort of Australia-wide forecasting. There would also be communications. So if you ever looked at a house and it has the sort of satellite dish for satellite television, and they're all it's just kind of pointing somewhere in the sky, and you're like, where's it pointing? It's pointing at an angle, the right angle, to a satellite in geostationary orbit. So the satellite is broadcasting that information. So if you've got satellite TV, that's where it's coming from.
So you don't have to keep adjusting the satellite on your house.
Yeah, that's right.
Antenna.
Yeah, no, because that satellite stays fixed relative to the Earth because it's moving at the same rate. That's why when they install it, it doesn't have any moving parts. It just they adjust and they point it in the right direction, and away they go. You've now got satellite television.
So there's some uses. What about the last kind of satellite I think of in terms of kind of having weird orbits are GPS satellites. So where are they orbiting in this whole lob of satellites?
They're about halfway in between. So they're about 20,000 kilometres up. That's called medium Earth orbit, I guess you would call it.
And how does that one satellite just know where I am? How can it calculate and tell me where I'm moving about?
Yeah, interesting question. The way GPS works is incredibly clever, and it's actually the other way around. That's why you need to have what's called a GPS receiver. So it's actually your phone that does the maths to figure out where you are. The way it works is the GPS satellites work on time, and the GPS satellites, they know where they are. They're calibrated using many, many reference points, distant galaxies, distant stars, radio signals, things like that. And basically what they're doing is they're constantly just broadcasting where they are. And here I am, here I am, here I am, here I am. And also they have very accurate clocks on board. And they go, here I am, here I am, here I am, and this is the time. And I'm at this point at this time. And your phone, it listens out for that. And if it picks up if it picks up a signal and it knows where the satellite is and it knows the time on the satellite, well, it takes time for that signal from the satellite to travel out and reach your phone. And then your phone goes, well, that's the time on the satellite, but it's this time now. So I know how far away you are because I know how fast light travels. So it works out where the distance is to the satellite, and it does that for multiple different satellites. And it basically, if this satellite's here and that satellite's there and this satellite's over there, the only place I can be is in the middle. And by doing that with multiple satellites, that's how GPS can work out where you are. Mm-hmm. And that's why GPS needs to be quite high off the ground so that your phone can see lots of different satellites. Because if GPS was really low and moving at 27,000 kilometers an hour, you would only see a satellite for just a few seconds and it'd be out of range of your sight.
Yep.
So you'd need to have hundreds of GPS satellites. So yeah, you put them 20,000 kilometers up, you can get away with only 24 of them, which is, or I think there's 31 of them there now, but you don't need very many of them.
And we're talking about all these heights. So we're going, low Earth orbit up to 1,000 kilometers, and then these geostationary orbits are 36,000 kilometers away. That sounds very far to me. But for scale, how far away is the moon, to put that in perspective?
Yeah, good question. So yeah, the moon is typically about 10 times further than that.
Yeah.
So
we're not near the moon yet.
No, not even not even close. Yeah. But it is worth pointing out the moon is a satellite as well of Earth.
It is a natural satellite.
It's a natural satellite. We didn't put it there, but it goes around the Earth.
But it's not stationary. It's moving slightly.
Yeah, it is, but it's moving slower than the Earth spins, which is so. Yeah, interestingly, if you're closer than 36,000 kilometers an hour, you need to move faster than Earth spins, which is why the low Earth orbit satellites race around the Earth once a day. If you're at exactly 36,000 kilometers, you move at the rate the Earth spins, and if you're further away, you move slower. And that's why the moon rises in the east and sets in the west, because of the Earth spinning, but over time moves from west to east.
Yeah.
The west to east movement is the movement of the moon, but the east to west movement is the spinning of the Earth.
Yeah.
It's not a very well structured sentence, but if you understand it, you understand it.
Excellent. I'm glad your job is to communicate science. That's the attitude you have.
Yeah.
But also the moon is slowly moving away from Earth over thousands of years. Is that because it's just moving a little bit too fast and it's just slowly getting out of its orbit, and that's why it's moving away from Earth and eventually will be gone? Or is that just because of the sun? Or
it's because of Earth's flexibility. Like the oceans kind of slosh around and the oceans pull on the moon, and the moon pulls back, and the force of gravity between the Earth and the moon is not straight up and down. There's a little bit of sideways component that drags the moon along, and as it drags the moon along, a bit like when you're dragging anything along, you're adding speed to it, and as a result the moon speeds up a bit. But then what does it happen when it speeds up? It moves further away. Yes.
So not only do we sometimes lose our satellites we put up there, we're one day going to lose our natural satellite as well.
Yeah, I think the sun will consume us before that happens.
Oh, okay. Well, something to look forward to.
Yes.
So going back to the PSLV, so our third stage fuel tank, it looks kind of weird. I, for some reason, had it in my head that it would be like this metal, like a water tank, and it would be really smooth. But it doesn't appear to be made of like a tin can sort of thing. So what are we looking at?
Yeah, it's actually made mostly of Kevlar, which is like a high strength nylon based fiber that's all woven together, and it's almost, imagine wrapping a string around a bottle lots and lots and lots of times, and then somehow deleting the bottle, and you have this sort of shape left over. Yeah, there's this thing.
I've heard about Kevlar in like an army context. Is that same thing? Or?
Same thing. Well, yeah, because Kevlar is very, very, very strong. It can handle lots of tension, and so you can imagine if you've got a rocket engine literally firing, there's lots of hot gases, and basically a rocket is a controlled bomb. It's a bomb with a hole in one end, and the explosion goes out that one end and pushes the rocket in the other end. But the entire thing just wants to blow up. So you want to have a really strong material to hold it together. And so, yeah, you're right. And metal would be a good solution, and it can be used. Aluminium is often used, but metal is heavy, and Kevlar is a lot less heavy for offering similar strengths.
Really? I don't know why I would have thought it seemed heavier.
Yeah, I mean, there's still this empty tank still weighs 500 kilos. It's not, it ain't light. But for if you were to build it out of steel, it would weigh 3 tons, and you get the same performance out of it. So why not use something a bit small, a bit lighter? So yeah, rocket science is this huge trade-off between strength and efficiency versus being as light and as cheap as possible, because everything about rocket science is heavy and expensive, and so if you can make it light and cheap, all the better. But of course, safe being the important word too.
Yeah.
Now, the important thing to mention: the PSLV does not launch people. There's no people launched on it. Only spaceships. But there obviously are rockets that launch humans, and they have some pretty strict safety things. Right now, fortunately, that's still up to governments to decide whether or not it's safe to launch people on these things. There's as spaceflight becomes commercialised and private companies are put in charge of this stuff, you might have to worry about it. But for now, governments get the final say on whether people can go on these things.
Oh, good. Okay. Well, because I know the other thing to be concerned about with a fuel tank is kind of what they used to contain. Obviously, we talked about how it was a fuel tank, it's burned off all the fuel, but there are different types of fuel and they are different types of dangerous, I suppose you could call them.
Yes.
Do you want to talk to us about what type of fuel this fuel tank contained?
Yeah, we got lucky with this one. This one's actually a very safe thing to go near. This in particular is it's a type of fuel called a solid fuel. So there's 2 types of fuel: liquid fuel. We put liquid fuel in our cars, kerosene or gasoline. Whereas there are solid fuel, and you might even remember the solid boosters, the big white boosters on the side of the space shuttle. And this is an example of that. And it uses a solid fuel called hydroxyl terminated polybutadiene.
Oh, yes, that one.
Yeah, that one. Classic.
Rolls off the tongue.
It is worth memorising, actually, because...
Because it makes you sound smart? Or?
Yeah, it makes you sound smart. But also, it's basically the go-to fuel for just about every solid rocket. So the solid rockets that the space shuttle used were filled with hydroxyl terminated polybutadiene, or HTPB. Just stop saying that so many times. And it's mixed with an aluminium catalyst and oxidizer, and it's all sort of glued together into this sort of rubber-like material. So it's not rock solid, but it's kind of rubbery, and it can be cast into molds. So you assemble it and you melt it into a liquid, and then you pour it into the shape of your rocket engine, and it sets in that shape, and so then it fits perfectly. And so it's very handy to work with. It's not toxic, it's not poisonous, it's not hazardous. So of all the things, we lucked out with a rocket that's reasonably safe to go near. And it's funny because the second stage of the PSLV, which also drops into the Indian Ocean, is filled with an unbelievably toxic fuel called hydrazine.
Oh, I'm so glad we're putting that in the ocean. Is that?
Yeah. Well, if that had washed up on the beach, there was no way it would be on display for people to look at.
Oh, even though it's all been burnt out of the fuel tank, we still couldn't go near it?
Yeah, because they're just, trace residue, things like that.
Is that okay to be in our... there's 60 of them just in the ocean? That's all good?
That's why they're gambling on it sinking. And so this comes back to space pollution.
Right.
Yeah. Hopefully, it's all fine. Now, to be fair,
that's good. That's what we should base this on. Hopefully, it's all fine.
Well, remember, big sky theory, satellites will never collide, space junk will never be a problem.
Big sky theory sounds like something Big Pharma would come out with. I don't know. That's the vibes I'm getting.
If the second stage had washed up, I imagine it would be dismantled and sent back to India for cleaning up because, the hydrazine fuel is very, very toxic. And
because I know there was kind of discussion of whether ISRO was going to get this third stage back, and they kind of went, we're not going to pay to transport it back. And we went, well, we'll have it then because that's cool. But if it had been that second stage hydrazine one, would we have been a bit more like, actually, no, you're going to need to come grab this and it's your problem. You're going to need to take care of it.
Yeah, basically. So the sort of go-to rule of thumb is that space junk is the responsibility of whoever put it there.
That seems like a decent rule of thumb.
Yeah, and so, Australia could have said, no, we're not having this, come and get it. But in this case, my understanding is it was Israel's like, we don't really want it, and Australia was like, oh, we can probably make something cool out of it, so we'll have it. So that's the thing. But yeah, if it was something really dangerous, like a second stage, then we wouldn't. I'm pretty happy we got this one.
Well, that's fortuitous then.
Can I tell you a cool story about space junk falling back to Earth, though?
Yes.
So we mentioned that ISRO moves the fourth stage of the PSLV to a graveyard orbit out of the way. Some spacecraft do have just enough fuel, not to just get out of the way, but to to deorbit themselves, so they can actually push themselves back to Earth and deliberately burn up in the atmosphere.
Is that just to avoid the space junk issue, or is there another reason for that?
No, that is to avoid the space junk issue. So SpaceX actually often do this.
Oh, good.
Which is pretty good because they're the ones doing most
Putting
of the
a lot of
launching at
stuff
the
up
moment. This is just the rocket body, obviously, and as does another company called ULA. It's called a deorbit maneuver. But of course, you don't want to just deorbit and wipe your hands of it, and then suddenly it comes crashing down over a city.
In the middle of a city.
Yeah. So what you can do is you can, by choosing the time of your deorbit burn, you can very carefully, you can actually choose where it's going to crash down. And obviously you want to do that away from people. And there's a point in the Pacific Ocean, and you can draw a line in any direction, and it's...
Is this the Bermuda Triangle?
No, different ocean.
I don't know where the Bermuda Triangle is, so...
But it's the furthest point from land in any direction. Doesn't matter which way you go. Yeah,
Is this Point Nemo?
It's Point Nemo.
Yeah, okay, I got there in the second one.
Yeah, well done. Which is awesome. There's a place called Point Nemo, which is it's about 2,500 kilometres further east of New Zealand, about halfway between New Zealand and South America, but also a bit further south towards Antarctica. And there's just nothing there. Even there's not a lot of marine life. Apparently, the currents just don't work out. There's not a lot of nutrients in the water.
Is that it? Or is it because you keep dropping fuel tanks there and nothing?
Which came first? So as a result, that's where a lot of spacecraft. It's a spaceship graveyard. They splash down in the water there, and if there's anything left, it sinks. And eventually, the International Space Station will end up there.
Oh,
so yeah, SpaceX.
A true shipwreck.
Yeah, SpaceX has been contracted now to be in charge of deorbiting the International Space Station, and they will likely splash it down at Point Nemo. It's where the Russian Mir space station came down. I remember seeing that. Do you remember seeing that one come down?
When was that?
2001. Of course you didn't.
When I was a child.
But so ironically, yes, I'm sure there's a joke in there about finding something there. But
no, I can't think of it.
Can't think of one, no. So that's it for this special episode of Please Look Up, all about the Polar Satellite Launch Vehicle. If you have any questions, please let us know. You can reach us on Instagram at ParticleWA, and we'll answer them in future episodes. Thanks for being here, Amanda.
Thanks for having me.
And thanks for listening. If you want to hear more interesting space news, check out the website particle.scitech.org.au for more information.